Welcome to Visual Algebra Lecture 4.5, Quotients of Quotient Groups. By the fundamental homomorphism theorem, we know that every homomorphic image is a quotient. By the correspondence theorem, we know how to characterize the subgroups of a quotient and which are normal. The next question to ask is, how can we characterize the quotients by these normal subgroups? In other words, what can we say about the quotient of a quotient group? This is answered by the third isomorphism theorem that I call the fraction theorem. It has very aesthetically pleasing interpretations, both in terms of subgroup lattices and of Cayley graphs with nested shoeboxes, cosets. You won't see these anywhere else. Once we gain this intuition, we'll prove it, which is surprisingly straightforward. Let's get to it. Thus far, we have seen the first two of the four basic theorems about homomorphisms and their structure. These are commonly called the isomorphism theorems. The fundamental homomorphism theorem says that all homomorphic images are quotients. So the natural question to ask is, what can we say about the structure of a quotient group? The correspondence theorem, which comes next, characterizes the subgroups of quotients, including which ones are normal. That was in the previous lecture. Now that we understand what the normal subgroups of a quotient are, it's natural to ask what happens when we quotient out by one of those normal subgroups. And that answer is given by the fraction theorem, which characterizes quotients of quotients. Finally, the diamond theorem will characterize a certain duality of the structure of subquotients. And I think it's best to just wait until the next lecture to explain what I mean by that. But now I'll just tell you that it builds off of the correspondence and the fraction theorem rather nicely. These theorems all have analogs for other algebraic structures like rings, vector spaces, modules, Lie algebras, and more. And all of these theorems on their own, especially the last three, can look messy and unmotivated purely algebraically. However, all of them have beautiful visual interpretations, especially involving subgroup lattices. In this lecture, we will focus on the fraction theorem. Let's quickly recap to catch up to where we are, and this will also help give some extra context and motivation for what's coming next. 2 lectures ago, we studied the fundamental homomorphism theorem, which says that the group G, the domain, mod the kernel, is isomorphic to the image of phi. And in that lecture, I said you can extend this somewhat. So here's the group G. If you modify the kernel, you get V4, and that's isomorphic to the image. But this sits in a larger group, so if you relax the condition that this relabeling isomorphism from the quotient to the image is an isomorphism, you just say it's injective, then you get a decomposition of an arbitrary homomorphism into first a quotient and then an embedding. So I gave this exact slide after we did the fundamental homomorphism theorem. I also stated it formally like this with these two commutative diagrams. These are maps between the groups, and these are maps between specific elements. What I did not give then was this picture, because this is something that we now understand from the correspondence theorem in the previous lecture. That, in other words, if you take the quotient by a certain subgroup, you're basically chopping off the subgroup lattice and taking everything above it. So the quotient of Q8 by this subgroup looks like V4. And then this embeds into subgroup lattice of A4. So I think this is just a nice little picture to have in tandem with the one in the previous slide. Also, intuition that we now have from the first two isomorphism theorems. The quotient of a subgroup is just the subgroup of a quotient. And I don't just mean up to isomorphism. I mean the actual sets are the same. Let's see what I mean by that. This is the group SL2Z3 that we've seen a few times before. Has order 24. And I want to focus on two subgroups. One of them is going to be H up here, and the other one is going to be n down here. Both of these are normal. So H is a subgroup isomorphic to Q8. We can recognize the subgroup lattice. And so this is H, this is N. And notice that if we take the quotient of the subgroup, that is isomorphic to V4. It is an order 4 subgroup consisting of cosets. To summarize, this is a quotient of the subgroup H by N up here. On the next slide, I want to show you a similar picture that illustrates the subgroup of a quotient. So we're going to first quotient out by N, and then take this subgroup, and I claim we're not going to only get the same shape lattice, but we're going to get exactly the same lattice. That is subgroups of G mod N. So the quotient of G by N, so this is N mod N, and this is H mod N by the correspondence theorem. Looks like this. You should recognize this as the subgroup lattice of A4. And if we take the subgroup of this right here, then once again, we get the same thing. The subgroup of a quotient was exactly the same as the quotient of a subgroup. This is a characterization of the isomorphism theorems that really isn't given that much light of day, I think. A lot of people don't think of it this way. And another way to think about it is saying that if you have a group and you have two normal subgroups, you can think of the operations of taking a subgroup at one and a quotient at the other, and those two operations commute. And those of you who are familiar with matroids, kind of a generalization of graph theory, and it's a field in discrete geometry, you may have heard of the concept of deletion and contraction. And those operations commute. That's a fundamental property of matroids. And there's a way to describe a matroid with a big graph like this, a labeled Boolean lattice, and deletion corresponds to taking sub-lattices, and quotients correspond to taking, or to chopping off lattices, just like this. And the idea that the deletion of the contraction is the contraction of the deletion has a similar interpretation in terms of chopping lattices. But there's no real algebraic reason for why this is true. I just think it's a neat connection. So now that we have discussed taking quotients of a subgroup and subgroups of a quotient, what about taking quotients of a quotient? So this is a quotient group, and this subgroup is normal. So let's call this G mod N. So what is G mod N mod H mod N? So cosets of cosets. I don't know if that's hard for you to wrap your head around. That you're not alone. But let's look at this, and this group here has order 24, and the subgroup has order 8. So in a regular lattice, if you have a subgroup of order 24 mod a subgroup of order 8, what you're going to get is a subgroup of order 3. And so that has to be C3. Is this possibly, in this case, going to be C3? And if so, why? The answer, of course, is yes. It's almost too good to be true. Not only is G mod N, mod H mod N, C3, it is isomorphic. Well, the reason why it is because it is isomorphic to G mod H, which is the original group mod the original subgroup. It's almost like you can cancel these ends, like a freshman would in college. And some books actually call this the freshman theorem because this is what a freshman would do. They would look at this and cancel the ends. I don't like to call it that because freshman is a US-centric word, and people in Europe and other parts of the world don't necessarily know what that term means. It means someone who's in their first year of either high school or college. Let's say a bit about this fraction theorem. The correspondence theorem characterizes the subgroup structure of the quotient G mod N. In particular, it says that every subgroup of G mod N is of the form H mod N, where H is between N and G. Moreover, if H is normal in G, then H mod n is normal in G mod n, and that's actually an if and only if statement. In this case, we can ask, what is the quotient group G mod n mod H mod n isomorphic to? And that is the fraction theorem. Formally, given a chain of normal subgroups of G, where n sits in H, which sits in G, G mod n mod H mod n is isomorphic to G mod n. Here is a picture of that for the semi-abelian group of order 16, SA8. And if you're just tuning in, I devoted an entire lecture to this in Chapter 2, and it came up in Chapter 3 as well. So basically, here's how you should think of the fraction theorem. When you take the quotient of G by n, you're chopping off the lattice at n and taking everything above it. So here's what that quotient is. And this subgroup lattice you should recognize as C4 cross C2. So that's what G mod n is isomorphic to. Now here, if you take the quotient by H, then you're chopping off the lattice here and you're getting this lattice, which you should recognize as the Klein 4 group V4. And the fraction theorem just says if you first quotient out by n, you get this, and then you quotient out this quotient at this normal subgroup, then you get the Klein 4 group. In other words, up to isomorphism, it's the same thing as had you just quotient out by H to begin with. In some sense, the correspondence theorem says that taking a quotient amounts to chopping off the lattice at a normal subgroup, and the fraction theorem says taking a quotient of a quotient, in other words, taking a quotient twice, amounts to chopping the lattice off twice. But that's the same as if you had just chopped off the lattice at the larger group right from the start. Do you see why I insist that the fraction theorem comes after the correspondence theorem, even though most books do them in reverse? Here's a little more detailed picture of the fraction theorem and the same group G with normal subgroups n and h. If we quotient out by n, then the resulting lattice looks like this, which we recognize as C4 cross C2. But then if we take this quotient, by the correspondence theorem, H mod n is normal because H is normal in G. And we quotient out by that, now we actually get a quotient consisting of cosets of cosets. The actual elements are cosets, and within those cosets are smaller cosets. I know that's hard to visualize, but bear with me. I'll show you a picture soon. But for now, just recognize that this is the subgroup lattice of V4. And what the fraction theorem really says is that this quotient of quotient group here has the same structure as just the original group quotiented by H. Did I scare you on the previous slide when I spoke about cosets of cosets and how I would give you a picture of that and explain it shortly? Well, here we are. So this is the same group of order 16, SA8, that we just saw. And this is like those shoebox diagrams that I did in the previous lecture on the correspondence theorem. N is a normal subgroup of order 2 that's contained in a normal subgroup H of order 4. Notice that G mod n consists of 8 cosets, these red little boxes, and that is isomorphic to C4 cross C2. H mod n, on the other hand, is the subgroup H of order 4 mod the subgroup N of order 2 that has order 2, so it's C2. It's literally just these two red cosets, which is a subgroup of the set of 8 little red cosets. Now, G mod H, so this original group mod H, consists of 4 cosets right here, and this is isomorphic to V4. And finally, G mod N mod H mod N, so that's what you get when you take these 8 cosets and you mod out by these 2 cosets, it's got the same structure as this. So here is a Cayley graph of G mod n mod H mod n. If you have to pause this at any time and sort of think about it and let it soak in, feel free to do so. I actually encourage you to do so. But G mod n mod H mod n, it's like by the fraction theorem, it's isomorphic to V4, and it literally is these 4 cosets of cosets. And G mod H consists of these 4 cosets, and these things are isomorphic. So did that help? If so, fantastic. I don't think it hurt. But if not, no worries, because the proof is really just algebraic. And let's do that now. So how are we going to prove this? Well, one thing we could do is set up a bijection between cosets of cosets and cosets of a different subgroup, but that sounds just dreadful. So this is like tailor-made for the fundamental homomorphism theorem. We also have 2 options. We could define a map from G mod n to, let's call it phi, G mod h, that has kernel H mod n, or we could define a map from going the other way, from G to G mod n mod H mod n, where the kernel is going to have to be H. Now, which of these things do you think we want to do? Well, both will work, but I don't like to deal with cosets of cosets, so I'm going to pick this one. So let's write that down. Let's define phi from G mod n to G mod h. That sends Gn, so that's one of those small red boxes. Actually, I'm going to write that with red. So in your mind, think that that's that little small box. And that's going to map to GH, and that's the big box that contains it. So think about, we're going to take one of these small cosets and send it to the big blue coset that contains it. Oh, and I need a little bar right there, because this is how it's defined. So first we have to define a map. One thing that I see when I grade exams is that some people try to prove it, and they might write down a map, but they don't actually say how it's defined, and that's essential. So first of all, this map is from a group of cosets, so we have to show that it's well defined. In other words, there are multiple representatives that we could use to denote G mod n. For example, there's an element right there, and there's an element right there in the previous picture. And it should make sense that, if we use either one of these, well, the box that it contains it is in the same big blue coset. But let's check this algebraically. So let's suppose that G1n equals G2n. So again, we have like a G1 here, and we have a G2 there. Then what does that mean? Well, that means G1 can be written as G2n for some element n in the subgroup big N. But then what? So if n is in big N, well, that's really the small box, well then n is also in the big blue box. So maybe I should say, write red on top of this, n is n. But that means that n is in H, because H contains n. Thus, G1H equals G2NH. But since n is in H, this is just H. So we can write this as G2H. And this thing here, remember, is just the image of G2n under phi. So this is phi of G2n. And this thing here is phi of G1n. And that's what we wanted to show, that if we had two cosets that are the same, then phi of those cosets is the same. So that shows that phi is well defined. Next, let's show this is a homomorphism. This is one of those follow your nose ones. Phi of G1n times G2n equals phi of G1, G2n by the definition of coset multiplication. And now by the definition of phi, this is just G1, G2h. And by definition of coset multiplication, this is G1h times G2h. And by definition of phi, this is phi of G1n times phi of G2n. So there's nothing to this, but it takes practice to do this. You're not going to be able to do it the first time you try. Onto is similarly straightforward, but I will say that when I grade exams, I usually have a few very bright students who say this is clearly onto, because every element in the codomain, GH, comes from the element GN in the domain. But then I have other people who say it's onto and try to prove it, and they don't prove it right. So I can't give credit to people who say it's easy or straightforward, even if I know that they know it, even if I know that they think it's straightforward. So if it is straightforward or trivial, you still got to write out a proof. It's even if it's one line. So for its onto, let's take something in the codomain over here. So let's take GH in G mod H. Then notice that phi, so what element gets mapped to GH? Well, it's GN. So that's why it's onto. Now, what about one-to-one? Just kidding. This is not one-to-one. It's going to have kernel H mod n. But I said that because when I give this on an exam, I will always get people who try to prove this as a one-to-one. And, you would hope that they would get stuck. But more often than not, they try to complete the proof or they write a fake proof. But if you're doing the fundamental homomorphism theorem, you don't want to show it's a one-to-one. You want to show that the kernel of phi is H mod n. So the kernel of phi by definition, this is also one of the follow your nose ones. It's let's take all things in the domain. So it's a set of all Gn in G mod n such that phi of Gn equals the identity element in the codomain. So that is H. And this is the set of all cosets. I'm just going to write Gn now, such that GH is equal to H, because that's what phi of GH is. So it's a set of all these things here, GH, that are equal to H. And so that's going to happen when G is in H by that boring but useful coset lemma. So this really is just the set of all elements Gn, where G is in H. And that, by definition, is GH. It's a set of all cosets of n where the element G is in H. And that's exactly what we want. So now the result follows by the fundamental homomorphism theorem. So by the fundamental homomorphism theorem, we are done. G mod n mod the kernel is isomorphic to the image. I want to finish this lecture with a visual that should look very similar to one that I just showed you 2 slides ago. And indeed it is, but it's a arguably less interesting example because this is an abelian group, and the quotient of the quotient in this case is the cyclic group C3. Less interesting than the Klein-4 group that we saw before. But I have reasons for showing this to you. First of all, this was one of the first visuals that I've seen, maybe in 2010. My friend Zach Tyler at Boise State, when we were at a conference, he showed me a picture of this. It was a lot like this, but there weren't any symbols. It was just, squares inside of rectangles, and I think the elements were dots instead of actual numbers. But he said that that's how he explained the third isomorphism theorem to his students, and I really liked it. So shout out to Zach. But also, more importantly, I have this in here because this is a ring. Whereas the semi-abelian group is not a ring because there's multiplicative structure but no additive structure. So in chapter 8, when we get to ring theory and we see the ring isomorphism theorems, this picture will come back. It'll have I and J in it for ideals, but the idea is that the isomorphism theorems don't just hold for groups, but they also hold for rings. So I'm not going to go over the details of these cosets and then cosets of cosets. It makes my head hurt a little bit too, but I encourage you to do it, to think about this and to explore it, and to keep this in mind because it will come back in chapter 8. Okay, so that's all for this lecture. We have one more isomorphism theorem left, which is the diamond theorem, which more often than not comes second, which I think is a mistake because the lattice interpretation of that is going to build off of what we've done in both the correspondence theorem and the fraction theorem videos. Okay, so you've made it this far. One isomorphism theorem to go. Don't go anywhere. I'll see you on the other side.